Glaciers, immense frozen giants that have shaped our planet for millions of years. But what happens when their waters melt and mix with the ocean? How does this affect the marine life, the ocean currents, and even our climate? Welcome to Ocean Science. Today we dive into the chemistry of glacial waters and its impact on the ocean. What is glacial water? Glacial water is some of the purest water on Earth. Locked for thousands of years, it lacks a unique chemistry composition. Unlike the seawater, the glacial water has low levels of salt, but has high levels on minerals like iron and silicate, essential nutrients for the marine ecosystem. But as glaciers melt and at an accelerating rate, this freshwater influx is disrupting the delicate balance of the ocean. A glacier forms when the snow accumulates over time, compacts into ice, and flows over its own weight. Glaciers appear white because they contain tiny air bubbles that scatter light, much like the snow. However, the pressure increases. These bubbles are compressed, allowing the ice to absorb more light. This absorption, especially for the red and yellow wavelengths, gives dense glacier ice its characteristic blue color. This formation can happen in different ways, so we will have different types of glaciers. We will have the alpine glaciers, found in high mountains, often flow from ice fields across peaks and ranges. The largest ones are in Arctic Canada, Alaska, the Andes, and the Himalayas. Valley glaciers originate from mountains or ice fields and flow down valleys, sometimes reaching the sea level. High water glaciers, valley glaciers that reach the sea, calming icebergs and providing habitat for seals. Piedmont glaciers form when valley glaciers spill into the floodplains, spreading into loops. Malaspina Glacier in Alaska is the largest example. Hanging glaciers left high above valleys when main glaciers retreat or melt completely. Their empty valleys are called hanging valleys. Circuit glaciers occupy bowl-shaped depression or mountainsides, usually wide rather than long. Ice aprons, small steppes glaciers clinging to high mountainsides, common into the Alps and New Zealand, and often to gradient avalanche. And finally, rock glaciers, mixtures of ice and rock that moves like glaciers, with ice either in the core or filling space between rocks. When glacier meltwaters enters the ocean, it creates a layering effect. Fresh water is less dense than seawater and tends to float on top. This process, called stratification, blocks the normal mixing of the ocean, reducing the exchange with oxygen and nutrients. In some areas, this leads to oxygen-deprived zones, affecting the marine life and the entire food chain. This impact also in currents and climate. The North Atlantic, for example, relies on a delicate balance between the cold and the warm water to drive the circulation. If too much fresh water enters, it can slow or even shut down this current, leading to extreme water currents worldwide. Some scientists believe that this could contribute to stronger storms, shift into the rainfall, and even prolonged droughts. Not all effects are negative. Some meltwater glacier carries iron, a key nutrient for the phytoplankton, tiny organisms that can absorb the carbon dioxide and form the base to the marine food web. This can create massive plankton blooms, temporarily increasing the ocean productivity. But not all the iron can be used by these organisms, and long-term effects of glacier rapid loss can be devastating. Glaciers are melting faster than ever due to climate change. What we do now will determine the future of our ocean, the weather patterns, and the marine ecosystem. Understanding the chemistry of glacial waters grasps us the biggest picture of Earth's climate system. If you want to explore more about the ocean, subscribe to the channel and stay curious. That is all for today. Thank you for watching. If you like this content, subscribe, and I will see you the next Saturday at 12 with the next video. Bye bye!